It's setting up now.
Yep.
Okay, now we are on live streaming on YouTube and also on Zoom. So let's start today's seminar. Today we are very happy to have Professor Josh Boswick from my department, the mechanical engineering at Clemson University. So Professor Boswick received a dual bachelor degree, one from physics, one from civil engineering and mechanics from University of Wisconsin, Milwaukee, in 2005. And then he finished his PhD in theoretical and applied mechanics from Cornell, finished in 2011. And then he joined Clemson as a faculty. Now he's an associate professor. His research is focused on the pattern formation, on interface and the surface tension driving phenomenon, and also on complex fluid and soft matter. And Josh, then I will leave the time to you.
Okay. Thanks, Zen. So let me get this started. All right. Okay, so yeah, thanks for the introduction, Zen. Happy to talk at the seminar. I think the participation has been great so far. Hopefully this can continue for the duration of the seminar. So the topic today is going to be elastocapillary instabilities in soft gels. And I'll sort of take you through a brief outline. So I'll talk a little bit about why we're interested in this problem, some of the backgrounds. The main theme here in this talk is going to be analogous hydrodynamic instabilities in soft gels. So a lot of stuff that we talk about has an analog in traditional fluid mechanics or traditional hydrodynamic stability. And we're interested in how these instabilities manifest themselves in sort of soft materials. So we'll talk a little bit about this. I'm going to focus on two specific problems. One is gel drop oscillations. Okay, and there's a couple different ways we're going to model these types of behaviors. One is through what I would call like lump parameter modeling. And I'll talk a little bit more about some of the work we're currently doing, talking about the viscoelastic response of a drop. And the motivation here is really to use this as what we're going to call a drop vibration rheometer. I'll talk in more detail about this when I get to it. The second sort of subtopic that I'll talk about is mechanically excited surface waves. All right. And these sort of come in two varieties. One are edge waves, and the second are Faraday waves. And we'll talk about the importance of these different types of waves and how they mix together, okay, and the conditions under which this occurs, all right? And finally, I'll end with some concluding remarks. So I want to first start off, acknowledge my collaborators, former students, current collaborators in the department. One, Xingchen Xiao, is up very early to join this presentation. Stephen Fredericks, Saiful Tamim, Philip Wilson, Chase Gabbard, and John Saylor, who's a colleague here in the mechanical engineering department. So a lot of the work that I'm going to talk about is their work, okay, as part of their either PhD or master's dissertations. And that work is published in these references that I show here on the screen. So if you're interested, I'm happy to send you copies of these articles after this talk. Okay, so the main motivation here is a few. Okay, so one is the recent advent of bioprinting technologies. Okay, so bioprinting technologies are very similar to inkjet printing techniques. Okay, where you force a fluid through an ink head, cause it to pinch off, and deposit on a targeted substrate. Really, the only difference between inkjet printing technologies and bioprinting technologies is the material that you're actually using. Okay, so in bioprinting technologies, you typically use what's called a bioink, and these bioinks have to basically be able to support cells, okay, and not damage them. All right, so typically bioinks are some sort of gel, either agarose gels or alginate gels. Okay, so the difference here is that these gels actually have a finite elasticity in addition to things like surface tension and viscosity. All right. Similarly, the manufacturer of flexible electronics deals with the interaction of a liquid with a deformable substrate. Okay, so here the substrate is actually pretty rigid. It has a high elastic modulus, but it's able to bend. Okay, so here we're interested in the interactions between the liquid drop via capillary forces and the deformation of these sort of thin materials. And there's other applications such as aerosol drug delivery. So for example, the deposition of droplets onto the lungs or other biological tissues, which involve drops with soft tissues. And then lastly, the mechanism of passive liquid transport. So shown here on the bottom, all right, is basically an array of drops which were sprayed onto surfaces with varying elasticities or elastic resistance. Okay, and what you actually see here is that the drops migrate to regions where the elastic resistance is small. All right, this is a phenomenon known as durotaxis. All right, so in elastocapillarity, there's basically two varieties. All right, so we're basically interested in systems where elastic forces and surface tension forces are comparable. All right, so the first variety that I'll talk about, and this will be mainly the focus of today's talk, is when you have an intrinsic surface stress. So if you have an interface that separates one material from another, that interface has an intrinsic surface stress or surface property. Okay, and in this case, the stress balance across the interface, tau 1 minus tau 2, basically balanced by that surface stress times the curvature. Okay, and also the gradient in surface stress if you have so-called Marangoni forces here. All right. In this case, surface stresses are important when the elastocapillary length is roughly order 1, and here we define the elastocapillary length as the surface stress over the shear modulus G. All right. The second case where people study elastocapillarity is what I would sort of refer to as soft wetting. So, for example, if you place a drop of liquid on a deformable substrate, all right, if that substrate is soft, it will sort of deform the three-phase contact line as shown here. Okay, this is called the Neumann's triangle, all right? And here you have a balance between the three surface tension forces, that of the liquid gas phase, that of the liquid 2 in gas phase, and that of liquid 1 and liquid 2, all right? So for a material that has zero elasticity, the forces must balance in all directions in this case. Now, in contrast, if you put a liquid drop on a rigid substrate, okay, they form a contact angle alpha that's defined by the surface tension sigma Lg, sigma Ls, and sigma Sg. Okay, and this is sort of familiar to those dealing with wetting phenomena as the Young-Dupre equation. So what we're really interested in the sort of intermediate regime where both surface tension and elasticity are important. So I just like to sort of illustrate the typical leg scales associated with these problems to sort of give you an understanding of how soft some of these materials have to be to observe elastocapillary effects. So I'd just like to do this by doing sort of a small scale analysis. So if you take a drop of water, let's say, and you put it on a substrate, all right, that water will induce a deformation on the size of the substrate, roughly the size of the elastocapillary length. And if that drop interacts with, let's say, a glass substrate with a shear modulus of about 70 gigapascals, all right, that deformation scale is basically going to be 10 to the minus 12, or basically subatomic scale. So this sort of justifies the fact that when people study spreading and wetting of liquids on rigid substrates, they don't worry about the elasticity because it's so trivially small. All right. Now recent work in the early 2010s by Gerson et al. Have shown that when you place a drop of liquid on an elastomer, okay, or a PDMS substrate with an elastic modulus of about 3 kilopascals, all right, that surface tension force can actually deform the substrate into what's called the wetting ridge. So what you're seeing here in the middle is a profile of the wetting ridge itself. Okay, and this wetting ridge has size of basically a micron. Now, the materials we'll talk today a lot about are Agarose gels, and Agarose gels have basically a tunable elasticity that can range from, let's say, 10 pascals to hundreds of pascals. So for example, if you have an agarose gel that has an elastic modulus of about 30 pascals, that can actually induce millimeter-sized deformations in the substrate. And these are actually big enough, okay, to induce fracture in that substrate. So here on the right, what I show is basically a starburst fracture that's formed when you place a drop of water on a really soft agarose substrate. And lastly, I would just sort of illustrate how soft these materials are once again by sort of stating that to generate the deformations on an agarose gel substrate on glass, that equivalent deformation, you basically have to load the weight of 40 Mini Coopers on the size of a 1 millimeter ring, okay, to get these deformations, which just sort of shows you the differences in scales here that we're talking about with these soft gels. All right. Within the field of elastocapillarity, I sort of further like to distinguish two different types. Okay, so one is basically bulk elastocapillarity, and the other is bendo-elastocapillarity, or bendocapillarity. All right. So when people talk about bulk elastocapillarity, they talk about the situation that I just discussed previously, where you're looking at the interactions of a liquid drop with a sort of a infinitely deep surface, or what can be considered an infinitely deep surface. In this case, the elastocapillary length is defined as the surface tension over the elastic modulus. All right. Surface tension can also induce deformations in much stronger substrates that are actually very thin. And this sort of belongs to the field of bendocapillarity, as shown on the right. So here, surface tension forces can actually deform much more rigid substrates, okay, provided that these substrates are very thin, all right? So in this case, capillary forces induce bending of those substrates, which can give rise to wrinkling, as shown on the far right, or sort of interesting self-folding capillary origami behaviors. So what we're really interested in, like I said before, is we're really interested in analogs of classical hydrodynamic instabilities, but for soft gels. And so I'll talk about a few of these. Okay, so on the left, we see the classical problem of Rayleigh drop oscillations. So in this case, what we have is we have a spherical drop of liquid, and that liquid drop has a surface that's endowed with a surface tension. And when you pluck that surface, it will vibrate in a characteristic mode shape, here defined by mode number n equals 2, n equals 3, and n equals 4. And then mode shape will oscillate with the characteristic frequency given by Lord Rayleigh in the late 1800s. In the middle is another classical example of a hydrodynamic instability, namely that of Faraday waves. So Faraday waves are basically formed on the surface of a vibrated fluid bath, all right? And Faraday waves are unique in the sense that they exhibit what's called a subharmonic response, which just means that when you vibrate the substrate at a frequency f naught, the waves actually form on the surface with a frequency f naught over 2, okay, or half the driving frequency. So the reason we're interested in Faraday waves is Faraday waves are basically a canonical example of pattern formation, all right, on interfaces, and we want to see how elasticity basically affects that pattern formation. And then lastly, the example of the plateau Rayleigh instability, which you see on the far right, which is seen in the flow of thin film on fibers. Here, cylindrical interfaces tend to beat up into drops separated by a characteristic wavelength, okay? And this is basically surface tension acting to minimize the surface area of this cylindrical column. So like I said, a lot of these instabilities that are classic have been observed in soft gels. So for example, in 2014, Serge Mora basically showed that if you take a container of a soft gel, all right, and you flip it upside down, all right, that surface corrugations will form, okay, and these surface corrugations basically depend upon the elasticity of the material and the depth of the fluid material within the container as well. Okay, so for those of you familiar, this is basically the classic Rayleigh-Taylor instability, which is driven by buoyancy. And similarly, in 2010, Moore and others also observed the classic plateau Rayleigh instability, but now in soft gels. Okay, so basically what you see here is a series of liquid cylinders, all right? And as you go down, basically you are decreasing the elastic modulus, all right? And once you reach a certain point, this elastic cylinder will become unstable to corrugations that are associated with plateau railing instability. So really the goals of our project or this presentation is going to be to talk about, number one, the Rayleigh drop oscillations, and number two, mechanically excited waves. All right, so we're trying to observe and analyze these types of analogous instabilities in soft gels. So the working material that we will use both in our experiments and our modeling is Agarose gel. Okay, and the reason why we like to use Agarose gel is that we like to sort of take a simplistic approach. All right, so there are many soft materials out there, and many soft materials exhibit complex rheologies. So our goal here is to basically look at elastocapillary effects. All right, so Agarose gels are nice to do that for the following reason. All right, so Agarose gels are tunable. All right, which just means that you can tune their elasticity basically by changing the concentration of the polymer you add to the solution, which is nice. All right, and the second thing that's nice is that Agarose gels typically have a storage modulus that's at least an order of magnitude, typically 2 orders of magnitude greater than the loss modulus. Now, from a practical point of view, that this just means that elasticity dominates and viscous effects are very, very small for these Agarose gels, at least on the time scale of the experiments that we're working with. All right. So what this means is that Agarose gels basically behave as what we'll call inviscid elastic fluids. Okay, so we'll be able to use a lot of the machinery for inviscid fluids, but adapted to include elasticity as well. All right, so the first problem we'll talk about is that of gel drop oscillations. And this really follows on the footsteps of the canonical problem of the Rayleigh drop, which was first analyzed in 1879. All right, so here we report the first observation of the elastocapillary transition in gel drop oscillations. And we basically use acoustic levitation to basically mimic a containerless process in terrestrial conditions. And lastly, I'll talk about the drop vibration rheometer, which we basically propose to measure the surface tension of soft gels. And I'll sort of mention that there's no current technique that allows you to measure the surface tension of a gel. So we think this technique is very novel. Okay, so let me just remind you, for those who don't know, of typical Rayleigh drop oscillations. All right, so shown here on the left is the oscillations of an inviscid liquid drop, and it's undergoing a L equals 2 mode shape oscillation. The frequency of oscillation is given here in the top, okay, where the square is basically proportional to the surface tension, the density of the material, and the radius of the drop. Here, K is the mode number. One thing you should note is that the Rayleigh drop frequencies are actually dependent upon 2 mode numbers, K, the azimuthal one, or no, K, the polar one, and L, the azimuthal one. And that the frequency or the spectrum is degenerate with respect to azimuthal mode number, all right? So typically to excite oscillations in a drop, okay, you have to force that drop at a given frequency. You can perform like a frequency scan. So shown here on the right is a frequency response diagram for an oscillating liquid drop. Okay, and basically what you see here is you see the series of resonances associated with these different mode shapes, the L equals 2, L equals 3, the L equals 4, the L equals 5. All right. Now, the shape of these response diagrams or the resonance curves tells you something about the material properties of the liquid. So for example, it tells you something about the size of the drop, it tells you something about the surface tension, it tells you something about the density of that liquid, all right? So that's basically the technique we're gonna use. Okay, so we're gonna use a comparison between experimental observations and a theoretical model to basically fit surface tension of soft gels as a free parameter. And that's gonna be sort of like our technique for measuring the surface tension of soft gels. Okay, so it's very difficult or nearly impossible to realize free drops in terrestrial conditions just because drops will typically fall, okay, under their own weight due to the force of gravity. All right, so there's a couple of ways you can get around this. One is you can go to outer space, okay, and where gravity is negligible and study drop oscillations there. all right? Or you can use the technique that we use, which is to ultrasonically levitate these drops and excite oscillations via amplitude modulation. So here what we do is we have an ultrasonic transducer and a reflector shown on the right, all right? So the ultrasonic transducer basically creates an acoustic wave that is reflected by the reflector back. And when you tune the distance between the transducer and the reflector just right, you can form a standing wave, all right? And when you form a standing wave, you can levitate a material, in this case, a drop, at the node of the standing wave. So what you're shown here on the left is just a typical drop that's being levitated in this ultrasonic field. Now, if we amplitude modulate that signal that we apply to the transducer, all right, we can basically excite surface modes at the prescribed frequency as shown here on the right. So what you see here is basically an n=2 mode being excited via amplitude modulation, okay, and it's undergoing the oscillation from t=0 to t=big T, its period. Now, the experimental procedure that we use to sort of quantify these oscillations is sort of schematically shown here in this diagram. I just want to point you to a couple important features, okay? So one is the figure shown down here on the right, okay? This is the procedure for how we make our gel drops, okay, which we can tune over a large range of shear modulus here from basically 2 to 200 pascals, all right? So basically what we do is we make a solution, all right, that has a density gradient, and we inject our Agarose gel solution that has not been gelled into this interface, all right? And basically what happens is that this gel drop, all right, will orient itself where its density matches that of the liquid, all right? And in doing so, we're basically able to make very, very spherical drops, okay? And we don't really have to worry about evaporation because these Agarose gel drops are contained within this immiscible mixture, all right? Now, the second thing I want to point your attention to is the basically the way which we monitor the size of the oscillations, okay? So once we have a drop levitated in the acoustic field, we pass a laser through that drop, okay? And that laser impacts a sensor on the other side. And basically what we do is we measure the occluded light from that drop throughout the oscillation, all right? And the intensity of that laser basically gives us a metric for how much that drop is deforming, okay? And that's basically how we're going to quantify the size of the drop oscillations. So when we do this technique, we can produce experimental frequency response curves as shown here, okay? So what you're seeing here is a measure of the deformation of the drop as it depends upon frequency. And what you see is you see this nice resonance curve, okay, with a peak frequency at omega n. So this is sharply peaked and has a characteristic bandwidth that we typically associate with the dissipation, all right? So what we're basically going to do is we're going to try to correlate our experimental observations with the theoretical model to infer what these material properties are, all right? So, but before we do that, we'll talk a little bit about the characteristic behaviors for these drop oscillations, okay? So for gel drops, both elasticity and surface tension are important, all right? And if this were a purely liquid drop, okay, its frequency would be proportional to sigma over rho r cubed, okay, the Rayleigh frequency. And if this were a purely elastic drop, it'd sort of scale differently. Okay, it'd be proportional to the elastic modulus over rho r squared. All right. So basically, what we can do is we can scale our experimental data with respect to the Rayleigh drop frequency. Okay, omega over omega sigma, and plot that against the elastocapillary number sigma over Rg. All right. And when we do that, we see a transition. All right, from elasticity dominated motion on the sort of small elastocapillary number regime to capillary dominated motion, which we see in the large elastocapillary number regime. And when these two sort of timescales balance, that is the capillary timescale and the elastic timescale balance, that's where we get the so-called elastocapillary transition. All right. And what you actually see here is precisely that. The elastocapillary transition for all of our gel drops, which fall nicely on this black curve. All right. Now, like I said before, we're really interested in using this technique to measure the surface tension of soft gels. All right. And I just want to sort of remind everyone who is not familiar with this, what are the existing techniques for liquids? So typically how you measure the surface tension of a liquid is either through a direct or indirect technique. So for example, here on the top left is a classic example of the Wilhelmy plate. Okay, so basically what you do here is you submerge this Wilhelmy plate, okay, into a bath, and you pull that plate out of the bath, all right? And here the basically capillary forces balance the weight that you measure, all right? And that sort of gives you a measure of the surface tension of the material, all right? Other methods such as it are sort of referred to as indirect methods, such as the pen and drop, okay? It's shown here on the bottom right. And for the pen and drop, basically what you do is you sort of correlate the shape of the drop, all right, with solutions of the Young-Laplace equation, all right, treating surface tension as a fit parameter, and that's how you get the surface tension of these materials, all right? I'd just like to mention that for both the Wilhelmy plate and the Denoy ring, so the classic ways you measure surface tension of liquids, these will not work for soft gels. And the reason why they will not work is that a gel is a solid, okay? So if you were to pull, let's say, a Wilhelmy plate out of a gel, or if you pull it out of a Denoy ring out of a gel, it would actually fracture that material. And when you fracture that material, you basically destroy the whole purpose or the principle of that measurement technique. And similarly, these techniques do not work for the pen and drop method either, because we don't currently have any existing method to predict the shape of a pen and drop that also has a finite elasticity. So our technique is pretty simple, all right? So like I said previously, we measure the frequency response of the gel drop oscillation, okay? And we get these nicely sharp peaked frequency response curves with the corresponding bandwidth, all right? And what we do is we apply a simple lump parameter model, okay? So for a drop, there's a few basic physics that are involved, okay? So one is that the drop has an inertia associated with the motion of the fluid, all right? And it has a resistance that's sort of proportional to both the surface tension as well as the elastic modulus, okay? So here, basically the surface tension and the elasticity sort of play the role of a spring constant in a sort of typical damped oscillator model. And then lastly, either a soft gel drop or a liquid also has a finite viscosity that gives rise to this bandwidth or finite dissipation that's sort of encompassed by a dash pot in this sort of basic model you see down here on the left, right? So if we treat this like a lump parameter model, okay, the frequency response, okay, to the damp-driven oscillator is given in this well-known form. So X over A is just proportional to the applied frequency omega, the natural frequency omega n, okay, and this damping factor, which we call zeta, all right? So what we do is we bring physics into these constants, okay? So for example, for the damping parameter zeta, all right, we associate this damping parameter basically with the dissipation of the Rayleigh drop mode, okay, which basically scales with the fluid viscosity, the size and the density in this way. And similarly, omega n is associated with the natural frequency, and we associate this omega n both with the surface tension and elasticity as shown here in equation 3. Okay, so basically what we've done is take a classic damp-driven oscillator model, associate physics for our problem with all these constants, all right, basically what we're going to do is we're going to take this theoretical curve for the frequency response and sort of fit that to our experimental data. And when we do that, treating surface tension and viscosity as unknown parameters, we get the following predictions. So on the left, you see the predictions for the surface tension, and on the right, you see the predictions for the viscosity of a soft agarose gel, as it depends upon the shear modulus. All right. And a couple things you want to note is number one are the intercepts. So at the intercept, the surface tension is precisely that of water, as we might expect, and the viscosity is similarly close to that of water as well. All right. So note here that both the surface tension and viscosity tend to increase as we increase the shear modulus. Okay. So that was a very basic model of drop oscillations in soft materials. And some of our more current work is to sort of extend these simplistic models to be a little bit more precise. All right. So basically what we've been working on is oscillations of a viscoelastic drop. Okay. So previously I said that we like to work with Agarose gel in experiment because it exhibits a very simple rheology. All right. It basically has an elasticity that does not depend upon the applied frequency. In practice, many materials exhibit more complex rheologies, and we're interested in applying our technique to those materials. So to do that, we need to develop a model that incorporates these more complex rheologies. So we do this by looking at the oscillations of a viscoelastic drop, all right? And we sort of start by reminding everyone that for an inviscid liquid drop, basically the oscillations arise from a competition between inertia and capillarity. This gives rise to a single time scale, basically the capillary inertia time scale as given by tau c, okay? And this, once again, gives rise to frequencies of oscillation predicted by Rayleigh. Now for a viscoelastic drop, the material exhibits a complex elastic modulus, mu, which has both a real part, mu prime, and an imaginary part, mu double prime. Here, mu prime is basically associated with the elasticity, and mu double prime is associated with the viscosity of the material, all right? And in this case, there's two additional timescales. One is the elastic timescale, tau e, and the other now is the viscous timescale, tau nu, okay, over which dissipation occurs in the system, all right? So in this case, we have a lot of different physics, all right? And we're basically going to consider the case where all these timescales are roughly equivalent. So we really want to look at these multi-physics here. So the model is pretty straightforward. Okay, so we take a spherical drop of material and we disturb its interface by some sort of small perturbation that has a harmonic time dependence with frequency omega. All right. This surface has a surface tension sigma, okay, and the material is basically characterized by a density rho and a complex modulus mu that is also frequency dependent. Now, there's two ways to analyze this problem. One is to sort of look at the natural frequencies, i.e. in the absence of an applied force, or to look at this as like a forced oscillations problem where we actually drive the system with a prescribed frequency given by the applied pressure here. And we'll sort of illustrate how our technique is useful for both. Now, for this case, it's a little more complex. So we're going to work with the actual field equations of linear viscoelasticity. Okay, here the stress T, okay, is related to the strain epsilon, all right, through the pressure P and the relaxation modulus G, all right. And we sort of treat this in the linear viscoelastic sense, i.e. the strain field is related to the displacement fields in a linear way. And for our problems, it's natural to define the displacement field in a polar coordinate system using r, theta, and phi as spherical coordinates. All right. So the governing equation, all right, for a linear viscoelastic material is given by what's the box term. So the divergence of the stress field should be equal to basically the inertia or the density times the second derivative of the displacement. Right? So this actually forms a closed system once we apply boundary conditions. And we can do a standard technique such as take the Fourier transform of the governing equation to basically get a frequency dependent governing equation as shown here in the bottom right. Keep in mind here now, mu is a frequency-dependent shear modulus, which basically characterizes the rheology. And for a soft gel drop, or sort of for a soft drop, the balance of normal stresses at the surface must be balanced by the surface tension times the curvature, okay, the Young-Laplace equation. And we also assume that that surface is shear-free, okay? So at this point, I'd sort of note that our analysis is applicable for any arbitrary rheology, but we sort of want to illustrate this on a couple classical examples, namely one, the Kelvin-Voigt model, okay, which is applicable for viscoelastic solids, and second, the Maxwell model, which is typically used for viscoelastic fluids. All right, so in each case, you'll note that the complex shear modulus has a relaxation time scale. In case of the Kelvin model, this is tau s, and in case of the Maxwell model, this is tau f. It basically describes the viscoelastic properties of the material itself. Okay. And we can compute a solution just by decomposing the displacement field, okay, into the potentials phi, q, and s, okay? And these potentials can be expanded using the spherical harmonics y. The procedure is actually pretty standard. We take these solutions, all right, we apply them to the boundary conditions, which gives us a linear system of equations for the unknown constants a, b, and c, okay? And basically the solvability condition for this linear system of equations gives us the nonlinear characteristic equation for the roots. This basically gives us the natural frequencies for the system. And here's some of the results. So the first sort of problem that we looked at was that of a sort of a linear elastic drop, okay, where we assumed that the drop had both a surface tension and elasticity, but that the elasticity was frequency independent. All right. And what you're seeing here on the left is a plot of the natural frequency as it depends upon the elastocapillary number. All right. And what you see is there's a transition for each mode, okay, from a sort of low frequency plateau to a high frequency plateau. All right. And the region where the change occurs, or region where the curve is increasing, is what we call the elastocapillary transition for that particular motion. All right. And what's sort of interesting is that if you look at the flow fields or the streamlines in these different regions, is that as you go across this elastocapillary transition, basically you get a set of vortices to appear, okay, that basically propagate deeper into the drop as you go from elasticity to the capillary dominated region, okay? So each mode has one of these transitions, and that transition point happens basically at a different elastocapillary number for each. So what I really wanted to get to is to sort of see how we might apply the technique that we introduced before for the drop vibration rheometer to a viscoelastic drop, all right? So when you look at a viscoelastic drop, we can consider the case of the Kelvin-Voigt model with rheology given up here, okay? Here, zeta s is the basically non-dimensional version of tau s, okay? It basically plays the role of like a solid Deborah number, all right? And has limits, zeta s equals 0, which is sort of like the purely elastic limit, and zeta s equals infinity, which is sort of like the purely viscous limit, all right? And we can compute the natural frequencies for these modes. The difference being here now is that the natural frequencies for a viscoelastic drop have both a real and imaginary part. Okay, the real part corresponds to the oscillation frequencies, and the imaginary part sort of corresponds to the decay rates associated with the viscous properties. All right, and what you actually see here is that if you plot the frequency against the solid Deborah number, all right, basically what you have on the left here, okay, are underdamped motions that transition to overdamped motions at a critical value of the Deborah number, okay? So we undergo this transition from underdamped to overdamped at high Deborah number, okay? And the case where the real part of the frequency is 0 corresponds to what's sort of classically referred to as critical damping. So this is one main difference between a viscoelastic drop and either a fluid drop or an elastic drop. Now, if we consider the problem of forced oscillations, that is, if we apply a time harmonic signal to our system, okay, we get a frequency response curve as shown here in the bottom left, okay? So here the system exhibits both a displacement and that is complex, okay, which basically means you can write it with respect to a magnitude and a phase, okay? So basically when you look at the frequency response curves, you're basically looking at the magnitude of the oscillations and not necessarily the phase. Okay, so typically the phase is associated with the dissipation and the magnitude is associated with the sort of real response. So we can basically apply this technique, okay, as a drop vibration rheometer for more complex rheologies. So we haven't done this in experiment yet, but we sort of performed a thought experiment or a numerical experiment, all right, where we've solved the system for a known rheology, okay, for a Kelvin-Voigt rheology as shown here on the bottom left. And that gave rise to a frequency response curve as shown here in the top left with a phase alpha shown here in the dash curve, okay? And basically what we can do is we can take this curve, all right, and back out the real part of the modulus and the imaginary part of the modulus, okay, at every driving frequency, okay? And if we do that, we can so-called measure the rheology from this type of experiment, okay? So this is typically what's done in your sort of standard cone plate rheometers, okay? So for every frequency, you measure the response of the material to a prescribed torque, okay? So basically what we're doing is we're doing something similar, but for drop oscillations. Okay, so the second part of this talk is going to be basically on mechanically excited waves. It's another type of classical hydrodynamic instability, and we're going to look at this for soft agarose gels. All right. So the schematic of the setup is pretty straightforward. Okay, we take a container full of material, in this case water, but this can be agarose gel. Okay, and that material fills the container, as you see up here. Okay, it fills it with a volume V, which makes a contact angle alpha, which is actually pretty important, and I'll talk about this in a second, with the container sidewall. And what we do is we vibrate this container with a prescribed amplitude and a prescribed frequency, all right? And for these different combinations of frequency and amplitude, we can excite surface waves as shown here on the right, all right? So the experimental technique we use to visualize these surface waves is to shine white light or collimated white light at the surface, okay? And basically capture this with a camera using a long exposure time. So when we use long exposure time imaging, basically what we're capturing is we're capturing the steady surface wave behavior of this oscillating pattern. And for these types of surface waves, we can characterize the wave response in the acceleration driving frequency space. Okay, so basically, like I said before, depending upon the acceleration and driving frequency, we see different types of behavior, all right? So shown here on the left is basically a simple schematic diagram of what's called a Faraday wave instability tongue, okay? So basically everywhere inside this gray region, you will observe a Faraday wave, or that the surface wave will oscillate with half of the driving frequency, all right? And everywhere outside of this Faraday wave tongue, we're gonna observe what we call edge waves, okay? And edge waves are basically axisymmetric waves, which exhibit a harmonic response, i.e. they oscillate with the same frequency as the driving signal, okay? And depending upon where we are in this sort of phase diagram, we get these different types of behaviors. So typically in the Faraday wave region, we exhibit typical modes like you see here on the right. Okay, so here we call this the 3-7 mode, the 5-2, and the 4-4 mode, all right? And we get these basically by 2D cross correlation with theoretical predictions where N and L basically play the role of the mode numbers of Bessel functions, okay, which are inherent to these types of cylindrical containers. All right. So for a typical wave to form in a cylindrical container, we can generate a model of what we call elastocapillary waves. I'll just sort of take you through the basic procedure here, all right? So for this case, we're basically going to assume that the flow field is irrotational, or that we can describe it using a velocity potential phi, all right? So everywhere in this domain must be governed by Laplace's equation, all right? And on the surface, we have a surface tension sigma, okay? And the jump in pressure from the material side to the gas side must be balanced by the Young-Laplace equation, all right? So basically, we can sort of perform a pretty classical analysis, okay, mapping the problem to the boundary, which basically gives us a governing equation as shown here on the bottom left, okay, which just relates the pressure to the velocity potential, okay, and the surface deformation y, all right, through the Onus-Organ number, which defines the viscosity, the Elastocapillary number, which basically defines the elasticity, okay, and lambda, which basically defines the non-dimensional frequency, all right? And we can solve this equation, okay, to generate the characteristic frequencies as they depend upon things like the bond number, the Onus-Organ number, the Elastocapillary number, and the aspect ratio of the system. I'm not going to talk too much about this, other than we're going to use this to compare it to our experimental results. Okay, so the first types of waves that we see are these sort of low driving amplitude edge waves, all right? So what you see here on the top left is a plot of the light intensity as it depends upon the radius of the cylindrical container. And basically what you see is you see regions of high light intensity and regions of low light intensity, all right, that describe the surface wave that we're seeing, all right? So we can basically quantify the disturbance of the surface by looking at the difference between the minimum and the maximum light intensity. So the maximum light intensity for long exposure time imaging occurs either at one of the peaks or the troughs of the wave, because you're always reflecting that light back because it's actually a flat surface. Now, the minima of the light intensity occurs at a node, okay, which tends to oscillate back and forth throughout the cycle, okay, or basically decreases that average light intensity, all right? So you can see resonance developing in the right image here as we change the driving frequency from 16.3 hertz to 16.6 to 16.9 is where resonance actually occurs. And this is basically just defined by the sharpness or blurriness of the image, okay? So for, let's say, for example, the 16.3 hertz image, okay, the image is very blurry and the wave pattern is not a typical standing wave, but rather it's a traveling wave, okay? Whereas for the driving frequency of 16.9 hertz, the pattern is very clear and it's very steady. And this basically typifies what we'll call a standing wave on the surface of this material, okay? And we can do this, okay, and observe the natural frequencies for, let's say, the n equals 1, n equals 2, 3, 4, and 5 modes as shown here on the second row, okay? And in general, what we do is we see really good agreement between our theory and experimental observations for these edge waves on Agarose gels. Okay, so here we've looked at edge waves on Agarose gels with elastic modulus anywhere from 1.2 pascals to 20.2 pascals. And the agreement is generally very good, generally within 5%, with some outliers, let's say up here at 9% or 7%. So we feel that our model is basically capturing the essential physics of these edge waves. Now, one sort of really interesting observation relates to the conditions under which you can actually form an edge wave, all right? So when you fill a container with a material, typically a meniscus is formed, as shown here in the top left image, okay? And this meniscus is actually sort of present for most materials, and it's actually pretty hard to get rid of, all right? So what we've actually found is that this meniscus is critical in the formation of edge waves, or we can actually suppress edge waves by suppressing this meniscus. So what we've done is we've done a set of careful experiments where we change this filling angle, okay, basically from an underfilled condition to an overfilled condition, and we look for the formation of edge waves as it depends upon this filling angle. And basically what you see is that if you fill this container perfectly flat, all right, or there's no meniscus, that you can suppress these types of parasitic edge waves no matter what the driving amplitude is, Okay, so the basic criteria for the formation of edge waves is intimately related to the meniscus, which we clearly show here. Now, whenever we have a flat interface and we do not excite edge waves, all right, we can excite Faraday waves. Okay, so this corresponds to being inside the instability Faraday wave tongue, shown a couple slides ago in gray. Okay, so for a Faraday wave mode, there's what you call a threshold acceleration. Okay, which just means that you can only observe Faraday waves above a critical driving acceleration. All right, and we've done that and observed basically the first 50 Faraday wave modes in a cylindrical container for water. And these modes are described by the mode number pair N and L, and we typically find very, very good agreement between experiment and theory. And so for, like I said previously, for the Faraday waves, okay, each mode has their respective Faraday wave instability tongue. Okay, so the way to read this diagram is this is a plot of the acceleration against the driving frequency. And each curve here on the left is a Faraday wave tongue for that prescribed mode. So for example, here, this purple tongue is the Faraday wave mode for the 1-3 mode, all right? So basically everywhere outside of this Faraday wave tongue, you'll not observe this type of pattern being formed unless you cross over into this tongue itself. So how this typically works in an experiment is that you have a prescribed frequency, okay, let's say 13 hertz in this case, and you increase the magnitude of the driving amplitude until you cross this threshold of the Faraday wave instability tongue, okay, after which you observe the formation of that particular mode, in this case, the 1-3 mode. Now, what you see here for water, okay, is number one, the threshold for these Faraday wave tongues is all very similar. So for example, if you look at the critical acceleration of the Faraday wave tongue for, let's say, the 1-2 mode versus the 2-1 mode, they all roughly fall within the same range, okay? Now we contrast that for a gel, okay, as shown here on the right, and you actually see an increasing trend for the acceleration threshold with mode number. So for example, the threshold acceleration for the 1-2 mode is much different than the threshold acceleration for the 2-1 mode, the 1-4 mode, 2-2 mode, and 2-0 mode, okay? And that threshold acceleration is actually many orders of magnitude, or at least an order of magnitude higher than that for water. And this basically illustrates that there's some sort of dissipation or elastic resistance that's occurring in the gels that is not occurring for the water. So we're really interested in elastocapillary effects. So what we can do is we can do a set of controlled experiments where we really focus on a single mode. In this case, we focus on the low frequency 1-2 mode and look at how the shape of that instability tongue changes with elasticity, all right? And on the left over here, I show you a series of Faraday wave tongues as they depend upon the shear modulus. So as you can see, for low shear modulus, G is equal to 0.27 pascals, all right, the frequency tongue looks like this. And for high shear modulus, G is equal to 12.2 pascals, the Faraday wave tongue has basically shifted upward and to the right, all right? And the reason why it shifts to the right, okay, is that as we shift to the right, surface tension and elasticity are both important, whereas on the leftmost side, only surface tension is important, all right? So basically, we go from a region that is capillary dominated, okay, to a region that is elasticity dominated. And this basically characterizes what we call the elastocapillary transition for these Faraday waves. So the last thing I want to talk about is sort of an interesting phenomena where we purposefully form a meniscus at the sidewall of the container, okay, and we enter into the Faraday wave regime. So when we do that, we can actually simultaneously excite both edge waves and Faraday waves. And their time dependence is such that the edge wave is harmonic and the Faraday wave is subharmonic. So this is sort of illustrated in the top figure, okay, where we prescribe a particular driving frequency, we excite an edge wave, and we increase the forcing amplitude past the Faraday wave threshold, where we find a Faraday wave to develop, and we get these beautiful patterns that are steady and develop as shown here on the far right. Okay, and these are actually pretty robust. Okay, as shown here on the bottom, we have a bunch of mixed modes for these different driving frequencies, as shown down here. Okay, so these exhibit sort of a complex temporal dependence. Okay, simultaneously exciting harmonic edge waves and subharmonic Faraday waves, which is actually very, very interesting. Okay, so that's sort of it for this talk. Let's sort of want to end with a few concluding remarks. So we're really interested in, like I said, analogs of classic hydrodynamic instabilities, and we've basically made the first observation of a number of elastocapillary instabilities, namely drop oscillations and Faraday waves. And we're sort of using this to introduce this concept of the drop vibration rheometer to measure the solid surface tensions of these soft gels. All right. And lastly, we sort of highlighted the role of the meniscus in exciting these edge waves in complex materials and how that gave rise to mode mixing phenomena. So I touched on this a little bit, but a lot of our future work is sort of focused on more complex materials. Okay, so we purposely have worked with Agarose gels for the simplicity, but in the future, we're going to work with more complex materials with complex rheologies and viscoelastic behaviors. With that, I'll end and ask if there are any questions.
Thanks, Josh. Very exciting work about the very detailed experiment observations and also the very rigorous theoretical analysis. So any question from our audience? So if you have a question, you can unmute yourself and ask a question to Dr. Boswick directly. So George, I have a question about the mechanical driving capillary waves. So when you set up the system, you mentioned the boundary condition actually is the meniscus. It's very important to generate the surface wave. So I'm wondering, in your experiment, do you consider the depths of the gels? If the depth will affect the behavior, or it doesn't matter?
Yeah, that's a good question. So the depth will affect the sort of resonance behaviors and the shape of the instability tongue for the Faraday waves. Okay, but with regards to if you're exciting a harmonic edge wave or a subharmonic Faraday wave, really the only criteria is that you have to have a meniscus. Okay, so whether that meniscus is formed with like a really small thin layer or a very deep layer, if you have that meniscus there, you're going to excite low frequency edge waves. So sometimes they're sort of referred to as parasitic waves. But yeah, in general, like numerically, the shape of the tongues definitely depends upon the depth, but the meniscus is sort of like a binary thing. You either have it or you don't. And so Xing Shen, who was doing these experiments, basically figured out that, you have to be very precise about how you get rid of this meniscus. So I think he was there with a syringe, either sucking out very small amounts of liquid or putting in very small amounts of liquid to make that interface perfectly flat to basically get rid of these edge waves.
Okay.
Hey, Josh, you have wonderful talk. This is Zhao Xu here. Yeah, it seems that you have studied everything, the surface waves. Just curious, what's your next step?
So the next step, I think, is to work with more complex materials. Okay, so if you go into most hydrodynamic stability books, okay, there's a whole catalog of capillary instabilities. So like drop oscillations, plateau Rayleigh instability, Faraday waves, things like that. And I think it's fair to say that most of these have now been observed in soft materials that have an elasticity. And I think one thing that I should really mention about the work that we're doing is that I would say one of the really novel parts is that we're doing dynamics. Okay, so previously, a lot of work in this field has, been really focused on statics. Okay, so how drops interact with soft substrates and like the static shape of the meniscus, for example, in a wetting ridge. The fact that we're dealing with dynamics and like dynamic phenomena is really one of the sort of thrusts of what we do. And obviously, when you have dynamic phenomena, the rheology of the material is very important, right? Because for a complex rheology, the frequency with which you drive these systems, it can behave much, much differently. So basically what we're doing now, or what we hope to do in the future, is, look at some of these analogs, but for materials with more complex rheologies to see if there's any new like physics that we can observe. And I think it's fair to say we'll probably expect to see new things. Okay. We just need to make sure we're working in the proper regime. Okay. So the nice thing about working with these Agarose gels is you can sort of tune it and you can create systems where you're investigating this transition. Okay. So if you're working with a complex rheology, you have to basically find a material where the time scales and everything sort of line up nicely, and you can look at that multi-physics. So finding materials that do this is sort of going to be one of the challenges in and of itself.
I see. Yeah. So just to follow up on that, do you think that that's a key challenge in synthesizing the gels by controlling the like loss modulus versus storage modulus ratio? So is there a challenge there? Because I'm not very familiar with that field.
Yeah, so we are definitely not chemists or polymer scientists,
Yeah.
So definitely in chemistry and chemical engineering, there's people who are experts at this and sort of making designer materials. We're actually more users, so like we're more interested in like the physics and the fluid mechanics. So we'll probably got to dig deep into that chemistry literature or find a collaborator that's interested in sort of designing such materials.
Yeah, as far as I know, I think those like polymer hydrogel, we can tune the cross-link, we can tune the entanglement by controlling the intrinsic properties. Yeah, I think I have read literatures on that. Yeah, just my 2 cents.
Okay.
Yeah.
Oh, hi, Josh. Hi, this is Zhao Yan from University at Buffalo. So very interesting talk. And so you kind of provide a lot of interesting patterns from your like observation on the polymers. So in fact, I just have a simple question regarding your prediction for the surface tension and the viscosity. So seems you observe a linear like a relationship between the surface tension and the viscosity and your shear modular. So I'm just curious if that linear like correlation is more like a general like a law for also applicable for other types of gels.
Yeah, that's a good question. I don't expect that to be linear. So I mean, I would sort of, I mean, you can even see the error bars are pretty large.
Yes.
So the main thing let me try to get back to this. So for example, as you go to higher elasticities, you can sort of see over here, the error bars are pretty big, right? So the thing that we were sort of encouraged with is this sort of regime over here for the small g, right? That we were able to sort of capture the water surface tension and viscosity values, right? Because when you have zero elastic modulus, this basically means that you have a Agarose solution that's almost all water, and you have a little bit of polymer in it. So it should theoretically exhibit the properties of water in general. But sort of to get back to your question, I would sort of say that when we're in this sort of high G regime, okay, we're sort of past that elastocapillary region, and these are basically like elastic waves out here. So I think there's probably more to study, and I wouldn't say I wouldn't say that this is wrong, but I would say there's probably more to understand in this sort of high G regime out here.
I see. So my last question about the viscosity. So maybe you have mentioned how you measure the viscosity for your kind of very soft gel. Maybe I just didn't catch it. Can you please elaborate on that point?
Yeah, so the viscosity, how we measure this is, so we have this experimental sort of resonance curve right here in the dots, right? And this sort of solid line is just a classical sort of systems level description of like a damped oscillator. Okay, so for a damp driven oscillator, you get resonance curves that look something like this. Okay, and that basically depends upon the natural frequency and basically like the dissipation and the bandwidth in your system. Okay, so basically what we did is sort of like a lump parameter model, if you think about it in like the maybe control system aspect of it, where we just took the natural frequency omega n from this control systems level perspective, and we basically put in the physics of surface tension and put in the physics of shear modulus. And the same thing is true for this zeta. This is like the bandwidth. We basically put in the physics of viscosity or dissipation. And basically what we can do is we can sort of take this experimental curve and take these parameters, mu, sigma, and g, as like fit parameters. And it'll basically fit the experiment to the curve. And basically the result is what we get here.
I see, I see.
Yeah.
Thank you very much for the further explanation.
Yeah, no problem.
So any other question? Okay, if we do not have full question now, so we will end today's seminar. If you have additional question later, you can contact Dr. Boswick directly. So his contact information is on our CFSM website. So thanks, Josh.
All right.